Hello students, welcome to my channel Engineers Academy. Kindly subscribe my channel if you haven't subscribed it yet. Now let's solve this simple problem. So again in this problem it is said that draw the shear force and bending moment diagram for the loaded beam and determine the maximum moment M and its location from the left end, right? So we are given this loaded beam and we are required to determine the maximum moment M and its location from the left end, right? So we will set our coordinate system. I will define my coordinate system from this left end, right? So this will be my coordinate system, right? So we will measure the x, the position of that moment, maximum moment M from this origin, right? So this is our coordinate system. So now to solve this problem, first what we need to do is that we need to determine the reactions at this point, right? Let's say here we have that pin joint, so let's say that this origin is point A and let's say at this end of the beam is point B, right? And let's say that at this particular point where the roller is in contact, let's say that this point is C, right? Or let's say that this point is B and let's say this point is C, right? So we have to determine the reactions at point A, at point B, right? And then we will proceed to draw the shear force and bending moment diagram for this particular loaded beam. So let's say that here at this pin joint we have, let's say, a y reaction, or let's say we have this is R1 and let's say this is R2, right? And since here we have that pin joint, so let's say that here we will have that horizontal reaction as well. So let's say this is R3, let's say. But if we look into this whole beam, right? So each and every force is acting in the y direction, right? If this is our positive y direction, right? So then we can see that if we take the summation of forces along x equals to 0, so we will have only this R3 acting in the positive x direction, right? So then this R3 will be equal to 0 since all the forces are acting in the y direction. So we can say that in the horizontal direction there is no reaction force at this particular point A. So we are left with R1 and R2. So now we will find this R1 and R2. So to find this R1 and R2, what we need to do is that we need to replace this distributed load by its corresponding resultant load, right? So let's say that this is our beam. So now here let's say that this is that point A. So here we will have that R1 reaction which will be acting vertically upward, right? And if I replace this distributed load which is associated with this triangular area, if you want to replace this, so let's say that this rectangular distributed load is, let's say, represented by let's say RA, right? So then we will find this RA, right? So then we know that this RA will be equal to the area of this triangle, which is equal to half, and the base is 2 meters, right? So I will write 2, and the height is 1 kilonewton per meter, right? So this will give us the force in kilonewtons. So this will give us 1 kilonewton concentrated resultant, which will replace this distributed load, right? And as we know that this RA will be located at a distance of 2/3 of this base distance, this 2 meter, right? As we know that the centroid of this triangular area is located at a distance of 2/3 of this length, which is 2, right? So now if I draw that RA here, right, we will have that RA, and let me find that 2 divided by 3 into 2. So this is 4 divided by 3. So this is 4 divided by 3 is 1 point something, right? So this means that this RA is located somewhere here, right? So here we will have that RA, and RA magnitude is equal to 1 kilonewton. Similarly, we can consider this rectangular area, and we can replace this rectangular distributed load by its corresponding concentrated load, right? So we can say that, let's say that the force, the concentrated load which represent this rectangular area is, let's say, RB, right? So then we can say that RB will be equal to the area of this rectangle, right, which is equal to this base, this is 2 meters, into this height, which is 1 kilonewton per meter. So we can add this is 2 into 1, so this will give us 2 kilonewton, right? So this is that RB, and that RB will be the line of action of this RB will pass through the centroid of this rectangle, right? And as we know that centroid will be located at a distance of half of this length, right? So this will be at a distance of 1 meters, right? So from this origin, this RB will be at a distance of 2 plus 1 meters, right? So it will be at a distance of 3 meters, right? So now let me draw that RB here, right? So that RB will be somewhere here. This is that RB. Let me write this RA here, right? So this is that RA, its magnitude is 1 kilonewton, and this is that RB, its magnitude is 2 kilonewton, right? And this RA is at a distance of, this is 2 divided by 3 into 2, so this is 4 divided by 3, so this is 4 divided by 3 is equal to 1.333 meters. And similarly, this RB is at a distance of 3 meters, right? So this is 3 meters. This is that 2 plus this 1 meters, right? And similarly, that R2 will be acting somewhere here, right? This is that R2, and 1.5 kilonewton force, concentrated force, is acting at this particular point C, right? So this is that 1.5 kilonewton, right? So now this is our free body diagram, and we can find that R1 and R2, right? So now if I apply the summation of the moment about this point B, here we have that point B, right? So if we apply the summation of moment about point B equals to 0, so as we can see that this R1 is producing the clockwise moment about that point B, so I will write minus R1, and the perpendicular distance of this R1 from that RB is 5 meters. This is 2 plus 2 plus 1, right? So this distance is 5 meters. So we will multiply this with 5, right? Similarly, this RA is producing the counterclockwise moment, so I will write plus, and its magnitude is 1, and the perpendicular distance of this RA from that point B is 5 minus 1.333. So I will multiply this with 5 minus 1.333. And similarly, this RB is also producing the counterclockwise moment about that point B, so I will write plus, RB magnitude is 2 kilonewton, and the perpendicular distance of this RB from that point B is 5 minus 3, so which is 5 minus 3 is 2, right? And similarly, this 1.5 kilonewton force is producing the clockwise moment about that point B, so I will write minus 1.5, and the perpendicular distance of this 1.5 kilonewton force from that point B is 1 meters, right? So I will multiply this with 1, and this will be equal to 0, right? So now this is minus 5 R1 and 5 minus 1.333. So this is 3.67. This is plus 3.67 plus 4 minus 1.5, and this is equal to 0. This is 3.67 plus 4 minus 1.5. This is 6.17, right? So we can write it minus 5 R1 plus 6.17 equals to 0, or we can say that R1 is equal to minus 6.17 divided by minus 5, right? So this is answer divided by 5. So this is 1.234, right? So R1 equals to 1.234 kilonewtons. So now we have determined this R1 and its magnitude is 1.234 kilonewtons. And similarly, if we apply the summation of forces along y-axis is equal to 0, and this is our coordinate system, right? This is our positive x and y coordinates, right? So this, if we apply the summation of forces along y, so we can say that R2 is acting in the positive y direction, R1 is acting in the positive y direction, and R1 magnitude is 1.234. Similarly, RA is acting in the negative y direction, so I will write minus 1, and RB is acting in the negative y direction, so I will write minus 2, and this 1.5 kilonewton force is acting in the negative y direction, so I will write minus 1.5, and this will be equal to 0. This is 1.234 minus 1 minus 2 minus 1.5. So this is equal to, we can say that R2 minus 3.266 equals to 0, or we can say that R2 is equal to 3.266 kilonewton, right? So we can write that this R2 is 3.266 kilonewton. Now to draw the shear force and bending moment diagrams, what we will do is that since the shear force and these are the internal forces and this is the internal moment, right? So what we will do is that we will consider the sections of this particular loaded beam, right? And we will consider these internal forces, right? So first we will consider the cutting section from x equals to 0 to x equals to 2 meters. Since at x is from x equal to 0 to 2 meters, this beam is subjected to this triangular distributed load, and from x equals to 2 meters to 4 meters, this beam is subjected to this 1 kilonewton meter distributed load, which is associated with this rectangular area, right? So whenever there is a change in the load for a particular beam at that until that particular point, we will consider that section, right? Since there is a change from that particular point, there is normally a change in the shear force and consequently in the shear force diagram, right? So we will consider the cutting section from x equal to 0 to 2 meters, right? So now let's say if I consider a cutting section until this point, right? So let me draw that cutting that section that we are considering, right? So at this point we will have that R1 and its magnitude is 1.234 kilonewton, right? And here we will have that triangular distributed load, right? Since we are considering this part of this loaded beam, right? So we will have some part of that triangular distributed load, and since we want to find this shear force, so we will have shear force somewhere here. If we are applying this R1 and this triangular load, so we will have shear force, the internal force here at this particular point. Let's say this is that shear force, which is represented by V, and here we will have that bending moment, that internal bending moment, right? So let's say this is that let's say that bending moment is represented by this M, right? Or let's say that this is V1 and this is M1, right? And these are the positive conventions of the moment and shear force, right, on the right hand side of cutting section. If this is the cutting section and if we are considering the shear force and the bending moment on the right hand side, so these are the positive conventions, right? This is from the book, from that Meriam and Kraige engineering static books, right? So we will consider this as the positive shear force and this as the positive bending moment. So now if we consider this cutting section, so since this is the part of that triangular distributed load, so we need to find the height of this triangle, which is not directly given. So for that, what we will do is that we will consider this large triangle, and this is the large triangle is from here, right? So we have this large triangle. So the base of that large distributed load, that triangular distributed load, is 2 meters. This length is this, if we consider this triangle, so the base of this triangle is 2 meters and the height of this triangle is 1 kilonewton per meter, right? And this triangular is some part of this triangle, right? So let's say that this is that small triangle. So let's say that the height of this small triangle is h, and the base of this small triangle, since we are considering this section, so the length of this section is x from this particular point. This is that point A, right? So the base of this small triangle is x, right? So if as we can see that both of these triangles are similar triangles, so we can apply the properties of similar triangles. So we can say that the h by x ratio will be equal to 1 divided by 2. The ratio of this perpendicular and this base will be equal to the ratio of this perpendicular divided by this base. So we can write that this h will be equal to 1 divided by 2 into x, or we can say that this will be equal to 0.5x. Now if we apply the summation of forces along y equals to 0 for this cutting section, right, for this diagram, so then first what we need to do is that we need to represent this triangular distributed load by its corresponding concentrated load, right? So let's say that this arrow represents that this triangular distributed load by its corresponding concentrated load. So again, this concentrated load will be equal to the area of this triangle, right? So that area will be, we can write that this area will be half times this base is x, and the height is equal to 0.5, right? So this is 0.5 x, right? So if I multiply this is half into x into 0.5 x, right? So this will be 0.25 x square, right? So I will write this as 0.25 x square. So now if we apply the summation of forces about the summation of forces along the y direction equals to 0. So since this is the positive convention for this shear force, so we will consider the downward direction as positive direction, right? This is plus V1. This R1 is acting in the negative y direction, so I will write minus. The downward direction is the positive direction, right? So this R1 is acting in the negative y direction, so I will write minus 1.234, and this concentrated load is acting in the positive direction, so this will be plus 0.25 x square, and this will be equal to 0. Or we can say that this V1, the shear force for the cutting section from x equals to 0 to 2 meters, will be equal to 1.234 minus 0.25 x square, and the units of this will be in kilonewtons, since R1 is in kilonewtons, right? And this is also in kilonewtons, right? So now as we can see that this V1 is a function of x, right? So this equation will give us the internal shear force values from x equals to 0 to x equals to 2 meters, right? So we can plot that shear force from this equation for x equal to 0 to 2 meters, right? So now we can plot that. Let me plot it here, right? So this will be about our positive x direction, this is in meters, right? And here we will have that shear force, right? And that will be, let's say that this is that shear force and this is in kilonewtons, right? So each box represents 1 meter, remember, right? So this is, if we find V1 x at x is equal to 0, so if we put x equal to 0 in this equation, so then we can say that this V1 x will be equal to R1. This is the magnitude of R1, which is equal to 1.234, right? So let's say that somewhere here is, let's say that at x is equal to 0, the shear force value is 1.234, and at x is equal to 2, if we put x is equal to 2 in this equation, so that will give us the shear force value at this particular point for this loaded beam, right? So if we put x is equal to 2 in this equation, so this will be 1.234 minus 0.25 x square, so x square is 4, so this gives us 0.234. So at x is equal to 0, that V1 x value is 0.234 kilonewton, right? And this is also in kilonewton. So at x is equal to 2 meters, we will have 0.234 value. And since, as we can see that this is a second degree equation, right? So this will be, the shape of this will be a second degree curve, right? Let me first find the shear force value at x is equal to 1 meter, right? So now if we put x is equal to 1 in this equation, so that will give us 0.984, right? So at x is equal to 1, this value is 0.984, somewhere here, right? So we will have a second degree curve like this, right? Since it's a approximated graph, right? So we will have the shape like this, right? Like this, right? I can show it to you people from the book as well, right? So we will have this kind of shape, right? So at x is equal to 0, the value is 1.233, or we can say this is 1.234, and at x is equal to 2, this value will be 0.234, right? So we will have this kind of shape, right? This is a second degree curve. So now we will apply the summation of moment about point A equals to 0, right? So to find that bending moment equation. for this particular section, right? So now if we apply the summation of moment about point A equals to 0, and since this is the positive convention, right, so we will consider the counterclockwise direction is positive, right? So we will write that this is plus m1, and this v1 is producing the negative moment about this point A, so I will write minus v1, and the perpendicular distance of this v1 from that point A is x, and this 0.25 x square is also producing the negative moment about that point A, so I will write minus 0.25 x square, and the perpendicular distance of this 0.25 x square from that point A is again, this distance is 2 divided by 3 into x, right? Since the centroid of this triangular portion will be located at a distance of 2 divided by 3 of this distance of this length, right? So we will multiply this with 2 divided by 3 into x, and this will be equal to 0. So we can write that this is m1 minus v1, and we have this v1 equation, right? So this will be 1.234 minus 0.25 x square into x. This m1 is equal to 1.234 minus 0.083 x cube. So now we have this bending moment equation for x equals to 0 until x equals to 2 meters, right? So now we can plot that moment equation as well. So again we can say that at x is equal to 0, the bending moment will be 1.234 kilonewton meter, right? The unit of this will be in kilonewton meter, right? So along this axis we have this moment which is in kilonewton meters, and along the x-axis we have that x distance which is in meters. This is 1.234 into x. Remember, this is 1.234 into x. So at x is equal to 0, the m1 is 0. Remember, right? So here we will have that 0 value. Now if we put x is equal to 1 meters in this particular equation, so we will get the moment value as 1.151, right? So let's say at x is equal to 1 meters, the moment value is 1.15. So we will have that value somewhere here. Let's say that this is 1.153 kilonewton meter. And similarly, if we put x is equal to 2 in this equation, this will be 2 to the power 3 . This is 1.804, right? So at x is equal to 2, the moment value is somewhere here, right? So again, it's a third degree curve. So we can approximately draw this curve like this, right? So now after this we will consider a cutting section for x equals to 2 meters until x equals to 4 meters. Since at x is equal to 4 meters there is abrupt change in the external applied load, right? So before erasing it, let me write this equation, right? So this curve is represented by this equation. Let me write that equation. This is 1.234 minus 0.25 x square, and this is represented by 1.234 x minus 0.83 x cube. Now we will consider another cutting section for x greater than 2 meters until 4 meters, and let's say that we consider this as the cutting section, right? So now if I draw it here, right, so this will be that cutting section, right? And here we will have that r1 again, right? And the length of this will be x again, since we are considering this as the origin. So now since we are considering this for greater than x, right, so we will have that complete triangular distributed load, and then we will have some part of that triangular distributed load, right? And since we are finding the equation for shear force and bending moment, and this is the right hand side of this cutting section, so this is the positive convention for the shear force, and this is the positive convention for the bending moment, right? So now again we will replace these distributed loads by their corresponding concentrated loads, right? So again, since it's a complete triangle, so then we can replace it by that same RA force, right? Or we can find that concentrated load. I can represent this triangular distributed load by its corresponding concentrated load, and that will be equal to 1 divided by 2 into the base. So the base of this triangle is this 2 meters, right? This 2 meters. So this base is 2 and the height is 1, right? So again we get it as 1 kilonewton, right? So we will write that this is 1 kilonewton, and then since this rectangular distributed load is, this distance is 2 meters and this is some part of that rectangular load, and the complete length of this cutting section is x. This is x, right? So then this rectangular distributed load is acting along the length which is equal to x minus 2. This whole length is x, and this triangular distributed load is acting until x equals to 2 meter, and then this rectangular distributed load will act along x minus 2 length, right? And this height of this is this rectangular distributed load is 1 kilonewton per meter. So if we represent this rectangular distributed load by its corresponding concentrated load, so then that will be equal to 1, the area of this rectangular distributed load. So the area will be 1 times this length, which is x minus 2, right? So now we have this diagram, right? So now if I simplify this, so we will have this diagram like this. We will have that R1, we will have that 1 kilonewton force, and this 1 kilonewton force will be at a distance of 2 divided by 3 into this 2 meters length, which is this 1.33 meters. So this distance is 1.333 meters, remember. And then this distributed load, this is 1 into x minus 2, and this distance will be how much? So this will be half of this x minus 2. So this will be half of x minus 2. Let's say that this concentrated load is at a distance of p, let's say. So now what I will do is that we will apply the summation of forces along y equals to 0, and remember we have that shear force here and we have that bending moment as well, right? So we will write that this is v, the direction of v is the positive direction, right? So this is plus v. R1 is acting in the negative direction, so we will write minus R1, and R1 magnitude is 1.234, and this is acting in the positive direction, this is plus 1, and this is acting in the positive direction, so I will write plus, and this is 1 into x minus 2, so 1 into x minus 2 is x minus 2, and this is equal to 0. So we can write that this is v minus 1.234 plus 1 plus x minus 2, and this is equal to 0. So now we can write that this is v, and this is minus 2.234 plus x equals to 0, or we can write that this v equals to 2.234 minus x, right? So from x equals to 2 meters until 4 meters we have this v of x equation, right? So now we can plot this equation as well, right? So let me separate these two graphs a little bit, right, so that we can draw the negative values as well, right? So now since this is from this is a v of x function for x equals to 2 meters until 4 meters, right? So now if I put x equals to 2 in this equation, right, so we will have that shear force value, right? So this is 2.234 minus 2, so we will have that 0.234 value which we obtained from this equation as well, right? So this value is 0.234, remember, right? And now from this equation, if we equate this equation 2.234 minus x equals to 0, so this will give us x equals to 2.234. So at x is equal to 2.234, the shear force value will be equal to 0, right? Since we have equated this equation equals to 0, so this means that at x equals to 2.234, the shear force value will be equal to 0. And as we can see that this v of x equation is the equation of a straight line, and the slope of that line is -1, right? So at x equals to 2.234, let's say that somewhere is that 2.234 value, right? The shear force value will be equal to 0. And if I put x equals to 4 in this equation, right, so this will be 2.234 minus 4. So at x is equal to 4, we will have the shear force value as negative, right? That is minus 1.766, right? So this is x equals to 3, 4, right? So minus, let's say that we have that some value somewhere here, right? So now since from x equals to 2, x equals to 4 meters, the graph will be a straight line, right? So we will join these 2 points directly, right? So we will have this curve, right? And now we will make these two graphs continuous like this, right? So we will have graph like this, right? So by hand I cannot draw the actual graph, but we will have the shape like this. Let me show it to you people, right? So we will have the shape like this. So this is the straight line equation. This straight line represent this equation, which is 2.23 minus x, right? Remember. So now let me write that this is represented by that 2.234 minus x equation, and the slope of this line will be -1, right? Now to find the bending moment equation for this particular section, so again we will apply the summation of moment about point A equals to 0. Here we have that point A. This end is at point A. We are considering this as the positive moment, right? So I will write that this is plus m, right? And as we can see that this shear force is producing the negative moment about this point A, right? So I will write minus, and this is the shear force equation. This is 2.234 minus x, and the perpendicular distance of this shear force from that point A is x, since the length of this section is x, right? So this is x. So we will multiply this with x. Similarly, this 1 kilonewton force is producing the negative moment, and this is also producing the negative moment. So I will write minus 1 into x minus 2, and the perpendicular distance of this concentrated load from that point A is p, and let's say that this p is, as we have discussed, that this p is equal to 2 plus half of this length. This length is x minus 2, so 2 plus half of x minus 2, right? So we can say that this is 2 plus, this is 0.5, so 2 plus 0.5x, and 0.5 into minus 2 is 1, right? So this is 1 plus 0.5x, right? So the perpendicular distance of this concentrated load from that point A is 1 plus 0.5x, and this 1 kilonewton is again producing the negative moment. So I will write 1, and the perpendicular distance of this 1 kilonewton force from that point A is 1.333 meters. So I will multiply this with 1.333. This is equal to 0. When we multiply these two terms, so we get 2 minus 0.5x square, and from this we get this. So if we simplify this, so we get this equation, and we can write that this m will be equal to minus 0.67 plus 2.234x minus 0.5x square, and the units of this will be in kilonewton meter. Now as we can see that this is a second degree equation, right? So we can plot for this is the equation for x greater than 2 meters until 4 meters, right? So now we can put x equals to 2 meters in this equation, right? So this is minus 0.67 So we get plus 1.798, right? So at x is equal to 2, that value is 1.798, and this is that particular point that we get this same 1.798 value from this equation as well, right? You people can verify it. This is 1.798, and at x is equal to, this is that very important point. At x is equal to 2.234, the shear force value is 0, right? So now if I put x equals to 2.234 in this equation, 2.234, so this gives us 1.8253, right? So let's say that this is that 2.234, x equals to 2.234, so we will have some value here as well, right? And at x is equal to 3, let's say if we put x is equal to 3 in this equation, so then this is 1.532. So this means that at x is equal to 3 meters, the moment value decreases, right? Which is, this is 1.153 and this is 1.7. So somewhere here we will have that value, right? So now this means that this moment decreasing like this, right? And then it will become 0 somewhere, right? So let me find, if I put x equals to 4 meter in this equation, so we get this as 0.266. So at x is equal to 4, this value is 0.2, so it will be somewhere here, right? So this graph is like this. We can check it from book as well, right? So we can say that at x is equal to 4, the moment value is positive, right? And then it will cross the x-axis, right? Now to find the equation for the shear force and bending moment for x equals to 4 meters until x equals to 5 meters, since at x equals to 5 meter we have this roller support, right? We have this R2 reaction. So again there is abrupt change in the external load at this x equals to 5 meters, right? So then we will consider the cutting section from the origin until that point, right? Until this arbitrary cutting section. So now for this we will consider a cutting section from x equals to 0 until this point, and this will give us the shear force and bending moment equation for x equals to 4 meters until 5 meters, right? So here at this particular point we will have that R1, then we will have that triangular distributed load, and then we will have that rectangular distributed load. This is from this point to this point, this length is 4 meters, remember this is 2 plus 2, right? We have no force here, right? So since we are considering the cutting section between x equals to 4 meters and x equals to 5 meters, so we will have this cutting section, we will have this free body diagram. And as we know that this triangular load is represented by that 1 kilonewton force, the area of this is 1 kilonewton, and this is represented by the area of this rectangular load, which is 1 into 2, so this is 2 kilonewton, right? So if I draw again only the concentrated loads, right? So we will have this R1 magnitude is known, which is 1.234. we will have that 1 kilonewton force, and we will have that 2 kilonewton force. So now if we apply the summation of forces along y equals to 0, and at this cutting section again, since we will have the internal forces, so we will have that shear force and we will have that bending moment. So again I will have this shear force and I will have this bending moment as well. So now if we apply the summation of forces along y, and this is our positive shear force convention, right? So we will write that this is plus v, this is acting in the negative direction, so I will write minus R1, which is 1.234, this is acting in the positive, so I will write plus 1, this is acting in the positive direction, this is 2 kilonewtons, so I will write plus 2, and this is equal to 0. So from this we get 1.766. So this is V plus 1.766 equals to 0, or we can say that V is equal to minus 1.766 kilonewton, right? So this means that from x equals to 4 meters to x equals to 5 meters, the shear force value is constant, right? And that is minus 1.766. And we get this same value, right? This is that minus 1.76 value from this particular equation, right? If I put x equals to 4 meters in this equation, it is 2.234 minus 4. So we get that same value minus 1.766, right? So this means that the shear force value will remain constant until x equals to 5 meters. This is x equals to 5 meters, right? So this will remain constant, and this value is minus 1.766 kilonewton, right? Similarly, if we apply the summation of moment for this section, for this free body diagram, if I apply the summation of moment about this particular point, which is point A, equals to 0, so then as we can see that this is our positive convention, right? So this is plus m, and this shear force is producing the negative moment, so I will write minus, and the shear force value is minus 1.766, and the perpendicular distance of this shear force from that point A is x, right? So we will multiply this with x, and this 1 kilonewton force is at a distance of that 1.33 that we already know. This is 1.333, and this is at a distance of, we already know that this is at a distance of 2. This is at a distance of 2 plus 1 meters, right? So this is that 3 meters. So this is at a distance of 3 meters. So this is minus 1.766. This is the shear force into x. This is minus 1 kilonewton into 1.333, and similarly this is 2 kilonewton, and this is again producing the negative moment, so I will write minus 2, and this is into 3 meters, and this will be equal to 0. So we can write this as plus 1.766 x. This is minus 1.333, and this is minus 6, and this is equal to 0. So we can write it as, and this will become minus 7.333, and this is equal to 0. Or we can say that this moment equation will be equal to 7.333 minus 1.766 x. So now if we take m equals to 0, right, so that this will give us the x value for which the moment will be equal to 0. If I equate this equation equals to 0, so we will get the x value at which the moment will become 0, right? So now we can write that this is, if we equate this to 0, so we will write it as 1.766 x equals to minus 7.333, and the minus sign will cancel out, so we will get 7.333 divided by 1.766. So x is equal to 4.15. So at x is equal to 4.15 meters, the moment will become 0. So this means that, and from this equation we can see that the moment equation is now a straight line equation, and the slope is minus 1.766, right? So now from this, and this equation is for x greater than 4 meters and less than 5 meters, right? So now if I put x equals to 5 meters in this equation, right, so this is 7.333 minus 1.766 into 5, so we will get this negative value, right? And that value is minus 1.497, right? So this is 1, 2, 3, 4. So this is x equals to 5 meters, and that value is minus 1.497. So this is somewhere here, let's say. So now we will join these 2 points, by a straight line, since from x equals to 4 meters until x equals to 5 meters the moment equation is straight line equation, and this particular value is how much? So this is this, here we have that value which is minus 1.497, and we can see it from here as well, right? This is minus 1.497 is approximately minus 1.5, right? So we can write it here is, we can write it is minus 1.5. So at x is equal to 5 meters the moment value is minus 1.5, and at x is equal to 5 the shear force value is minus 1.766. So now we can write the equation for this straight line as well, right? So this is according to 7.333 minus 1.766x. Now we will consider the final cutting section, right? So for x greater than 5 meters and less than 6 meters, right, we will consider again one another cutting section, and then we will consider this section of the beam, right? So let's say that if we consider the right hand side of this cutting section, right, and the positive x direction, the origin that we have defined for this particular problem is this point A, right? We are measuring the x, the positive x in this direction, right? So now if this section is located, if this cutting section is located at a distance of x from this end, if this length is, if this cutting section is at a distance of x, then the length of this cutting section that we are considering will be equal to the total length of the beam minus this x, right? So we can say that this length will be 6 minus x. The total length is 2 plus 2 plus 4, 5, 6, and so we are considering this small portion, so the length of this small portion will be 6 minus x, since we are considering, we are measuring x from this left hand side, right? And here at this particular point we have that 1.5 kilonewton external load, right? This is that point C, and since we are considering the left hand side of this cutting section, so the positive moment is then according to the positive convention, this is the positive bending moment, right? And the shear force, the upward direction of the shear force is the positive shear force value, and this is the positive convention, right? So now if I apply the summation of forces along y equals to 0, if we consider this cutting section, if we consider this section, right, so then we can say that this is the positive direction, so I will write v, and this is minus 1.5, and this is equal to 0. So from this we can say that v is equal to 1.5 kilonewton. So from this we can say that from x equals to 5 meters until 6 meters the shear force value is plus 1.5. So this means that this value of the shear force will shift to 1.5, right? So it will be somewhere here, right, like this, right? And then it will remain constant until x equals to 6 meters, right? So this is x equals to 6 meters, so then it will remain constant. So this is positive 1.5 value. And then if we apply the summation of moment about point C equals to 0, this is that point C. So then as we can see that this m is, this is the positive convention, so I will write that this is positive m, this is the positive moment about that point C, and this v is producing the positive moment as well, right? So I will write plus v into this 6 minus x. The perpendicular distance of this v from that point C is 6 minus x, and this is equal to 0. So we can write that this m is equal to minus v into 6 minus x, and the v value is minus 1.5, right? So we can write this as, this is minus into minus plus 1.5 x, and 6 into minus 1.5, this is 9, right? So I will write this as minus 9. So, and this is again in kilonewton meter. So now again we can see that this moment equation is again a straight line equation, right? So now if I put x equals to 5 meters in this equation, so we will get this exactly that same value, right? So if I put x equals to 5, so we get that minus 1.5 value, and if I put x equals to 6 meters, so we will get that 0 value, right? So this means that at x is equal to 6 meters, here we have that x is equal to 6 meters, then this moment value will become 0, and this we can join these 2 points since it's the equation of a straight line, right? So I hope you people would have understood this very lengthy problem, right? Such kind of problems are very lengthy, and I hope you people would have understood this particular problem. If you people want me to solve such more problems, and if you people think that these problems are worth liking, so do like my videos and share it with your classmates as well.